Hey everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. This is a very short interlude about oxidation reactions in our redox lecture. We're going to spend most of this lecture talking about reduction reactions, but we're going to say just 2 or 3 words about oxidation reactions. So there are some functional groups on organic molecules that can be oxidized. So those would be things like mercaptans. Those are sulfur-containing species. Those are the things that make salt marshes smell bad, and sewers and wastewater treatment plants and things makes them smell bad. Anilines can also be oxidized to nitrobenzenes, and phenols can be oxidized. So those are the functional groups you want to look for. Those are things that could undergo oxidation. Again, most organic chemicals were synthesized and designed to be used out in the world where there's plenty of oxygen. And if they were liable to be oxidized, that wouldn't be a great idea, because then they would just oxidize and they would no longer have their integrity. They would change their chemical form and no longer be what you designed them to be. So you design organic chemicals to be stable under oxidative conditions, i.e. the world. So there's really not that many that are susceptible to these kinds of reactions. So again, mercaptans, anilines, phenols. And the oxidizers that you might find important in the environment would be things like iron 3 and maybe manganese minerals. So this is just an example. This is from Alan Stone, who was one of my professors when I was at Johns Hopkins. Got my PhD there. Alan's a very, very nice man. In fact, I would say that I only finished my PhD because Alan Stone was nice to me. My PhD advisor and I had a falling out, and Alan is the man who saved me. So if it weren't for him, I wouldn't be here today. So Alan Stone did a lot of studies of this. He does a lot of work on reactions of chemicals at surfaces. So he was looking at a manganese 3 oxide type surface and reacting it with a phenol compound. The AR stands for aromatic. And so this phenol compound would float on up to the surface, and it would form a complex here, and this is what's called an inner sphere complex. Okay, so notice you lose the OH here and you lose the H here as a water molecule. And so this is directly bonded. The manganese is directly bonded to the oxygen, which is directly bonded to the phenyl, the benzene ring. And then once you're in that state, in that inner sphere complex, you can transfer the electron over. So you're stealing an electron from oxygen and giving it to manganese. Stealing electrons from oxygen is not an easy thing to do, right? Because oxygen is very electronegative. So that's why these are not very common reactions, but they do happen. So then this is actually what's called a phenoxy radical. It will be released out into solution, where it will go off to do all kinds of nasty things. That's why free radicals that's the word radical has a negative connotation, because radicals are liable to go off and do crazy stuff. And so we'll talk more in this lecture about what radicals do. But this is going to float off into solution and go do its thing. So you're left behind with a manganese 2 on the surface of your manganese 3 mineral, and it will dissolve because, generally speaking, the lower the oxidation state, the more soluble the metal is, in this case manganese. So manganese 2 is more soluble than manganese 3, so it will dissolve, and it will leave behind a new open site. So that's the kind of thing that can happen. The problem is that this is a really, really complicated reaction. It depends very heavily on pH, because that determines how much of the surface is protonated and how much of the phenol is protonated. It depends on the number of available sites. So it has, absorption kinetic or absorption isotherm that is definitely a Langmuirian type absorption isotherm, and it has kinetics that are similar to enzyme kinetics, Michaelis-Menten kinetics, where you have a limited number of sites, and once the sites are full, the reaction just can't go any faster. The rate at which these sites are regenerated after the reaction has happened, that's this state, this step right here. The affinity of the phenol. So what's the affinity here? How strong is this connection? And then and all of it depends on mass transfer, because it depends on this compound diffusing up to the surface. And so in the lab, you can control mass transfer by just shaking the thing, put it on a shaker or put it on a stirrer or something. But in the real world, maybe there's mass transfer because the groundwater is moving, so it depends on the groundwater flow velocity, for example. But there's all kinds of mass transfer just makes everything much more complicated. So that's all I'm going to say about oxidation reactions. Very short, but I hope you enjoyed it. And the next video will go on to, again, talking about some reduction reactions.